We are Group 10. Today we present assignment 1 that consists of 4 tasks related to multi-agent system and distributed computing. In this presentation, I will focus on task 1 and task 2. Before starting, I want to do a quick introduction to Mesa. It's a framework that we use in our tasks. Mesa is a Python framework for agent-based modeling. It allows us to define an autonomous system, an environment like a grid, a scheduler that activates agents step by step, and a visualization tool. Each agent acts independently, and global behavior emerges from a local decision, which is a key idea in distributed system. Let's move to task 1. Task 1 is a non-cooperative scenario. We simulate a parking lot where multiple cars independently search for parking space for limited time and then leave. Cars do not communicate to compete for limited share resources. Okay, now I can share my screen. As you can see, there I have agents. Okay, parking space agent, tree agent, car agent, model, and server. Okay, I can start the server. It takes some time. Okay. Okay. As we can see in blue, we are cars, parking space in green, and in red, obstacles like trees. So car agents, which move and search, parking space agents which can be free or occupied, and tree agents which act as obstacles. Agents are activated using random activation, so execution order changes at every stop. Each car behaves independently. If it's not parked, it searches for the nearest free parking space and moves step by step. Let's start it. Okay. The cars going to the park, and there is also the graph. So once a car parks, it stays there for 3 to 5 steps, then leaves and start searching again for new parks. And like the car that have the park is non, as I said before, is a non-cooperative system. Cars do not coordinate and congestion emerge naturally. We collect global metrics using a Mesa data collector, such as we can see in the graph, average steps to park, number of parked cars, and number of free parking space. The number of the cars and parking spaces are not hard coded to modified. It can be changed directly to the server parameter. There. We can move it to 5. Okay. If cars increase while parking space remain constant, congestion increases. If parking spaces increases, performance improves. This shows how resource scarcity affects non-cooperative distributed system. Yes. Okay. Let's move on to task 2. Okay. The same as before, we have agents, model, and server. So the focus of this task is the cooperation. We simulate 50 tasks with different duration and requirements, and 3 worker agents that must collaborate to complete them. Let's start the server. Okay, so we have worker agents in different color and tasks. The task agent representing a task and a worker agent representing a worker. Each task specified how many workers are required. If more than one worker is needed, the task progresses only if when all the required workers are assigned simultaneously. Each worker has a capacity of 2, simulating multitasking. When workers cooperate on the same task, they turn red, making cooperation visible. Let's start it. As we can see in red, different color for different agents. When a task is completed, it's turned in green and workers are released. The simulation ends automatically when all tasks are finished. To conclude, wait for a moment to conclude this task. Okay, different color for different agents, as I said before, cooperation in red. Okay, the task is finished. To conclude, task 1 demonstrates a non-cooperative system where competition and congestion emerge naturally, while task 2 shows how cooperation and synchronization improve efficiency. Together, these tasks illustrate how multi-agent system can model key aspects of distributed computing. Now it's turn to Yuja.
Hi everyone, this is our task 3. I'm Yuja, and this program is divided into 3 main parts. First, the text is spelled into sentence-based chunks here, and the second, clean and count words, and then the final one, our multi and single process. And in addition to this, I add one part, the visualize, make our comparison more clear. Okay, so let's come explain in detail. So the first, our sentence and base chunking function. The full text is spelled into individual sentence here. Using a regular expression, let the text sentence ending punctuation. This ensures each sentence remain semantically complete. And after sentence extraction, empty or invalid sentence are removed. Okay, so then our clean and count words. The function represents the core logic executed by each agent. First, the text is converted into lowercase void case sensitive counting, and then all non-alphabetic characters are removed using regular expressions. Okay, so after this, we download. Here we download the file and connect them, and then we do the single process execution. The cleaning and counting function is applied to each chunk one by one, and the execution time is measured to the serve as baseline for comparison. Okay, and then the multi-process execution. Each chunk is assigned to a separate process and processed in a separate and processed in parallel using the same cleaning and counting function. And after all process finish execution, the results are collected and summed in the main process. Okay, this is visualization, and we can see how it runs. Here we can find either use single process or multi-process. The result is same, but however, the time spent on are different, and even multi-process, the time spent on it is more than another one, and this can be more clear. The slower performance of multi-process execution is mainly caused by the process creation, overhead, and inter-process communication cost. Since the word count text itself is relatively lightweight, the cost of parallelization outweighs this parallelization outweighs these benefits. So I think this demonstrates that distributed computing is not always more efficient and should be applied selectively. Okay, so this is our task for International Weather Data Scraper. This project aims to build a stable and testable validated scraping system with three main goals. First, scraping real-time validate for international cities, and I choose London and Stockholm. And second, storing data in multiple formats and providing simple geographical interface for users. And for it, we use Kiwi, KiwiMD, and so on. Okay, so for the data storage, I use three methods. One, the text file, and this is the record information previously when I do the test, and the real-time database and the SQLite. Okay, and interestingly, initially I want to use my Circle service management, but I connected for so long time, but it doesn't function, so I give up it and choose another one. Okay, so then we will explain the code. So the first, the code is divided into clear map modules. The first, environmental setup inputs libraries such as request, SQLite 3, and something else. And then the open value map connect API. By the way, I should mention I use two weather sites. One require API and another doesn't require. One is open value map and another is value in, and which I will discuss later. Okay, so the database module initialized a SQLite and creates a weather table with fields like time, city, temperature, humidity, and visibility. And here it's for scraper. The scraping module contains two functions. One for data source, just I have set open weather map. It requires API, and another weather in. It doesn't require API. Okay, so both return dates in the same format include timeout control standardized units such as converting visibility and kilometers, just like this. Different source and temperature, humidity, visibility, pressure. Okay, so then the data storage class use three destinations, just like what I have said. And finally, the interface, I use the KiwiMD UI layout and combine with this. Okay, let us run it. And we can choose London or Stockholm, Stockholm, and Stockholm. Use open weather map. Okay, so we can find the new one. Oh, it's so cold. And meanwhile, we can find this one, Stockholm, the real time. And here, refresh, and the weather. Okay, so all three storage methods are verified. Data appeared correctly in the SQLite database and text file and Firebase console. And when we do the next test, we run it and choose London. Click it. Okay, so the test London different from the previous one. Okay, so that's all. Thank you so much.